So this week's tutorial is actually pretty near and dear to my heart. This is week 3, day 2. We're looking at the diffusion through a porous medium. And the case here is that we are going to look at how diffusion happens on different length scales. Okay, and this is going to be the first time that we're going to be looking at two different components put into the same model file, and there are reasons that we want to do this. So the idea is that we have this porous structure here. We're going to watch as it diffuses through here, and then we're going to take that result and modify it, homogenize it into a single effective diffusion coefficient. In material science, this is something called the multi-scale paradigm. The idea is that the diffusion going through the porosity, that porosity is at a very small spatial scale, whereas what we're interested in is a much longer spatial scale. So a good example is actually the clothes that you're wearing right now, right? If you put a drop of water on that, you would see it diffusing as the stain sets into your clothes, right? If you look at it through a microscope, though, you'll see that your fabric isn't actually a continuous medium. It's actually a woven structure of threads, and that stain is actually propagating and diffusing along those threads. But at our normal eye scale, we don't see that. All we see is the homogenized result. So that's what we're trying to do here. Now, the reason why we're putting that into the same model file is we want to be able to share some of our input parameters to clean things up. Otherwise, we have different files, they're going to be accessing different things. It's inevitably going to mess up, right? So remember that anything defined up here under your global definitions is going to be available everywhere in your problem, regardless of component, of geometric dimension, physics, whatnot, doesn't matter. It's going to be available. So up here in parameters are where you put in your general parameters, your diffusion coefficients, your other properties to do with the peak initial concentration, so on and so forth. You can also put in variables that are going to be common. In this case, all of the dimensions that we have are going to have x, the x coordinate. One is going to be 2D, one is going to be 1D, but both of them have x. So it's nice to put in our initial condition so that we don't need to put it in down below. Now, component number 1 is going to be our two-dimensional geometry, right? We've defined it in here. We've added on a couple of variables. These variables are unique and only accessible from within component 1. That's a little bit of a lie. There is actually a way that you can access it, but think about scoping, think about being object-oriented programming, and just take it that you are not able to. We might get to the super secret way later. Within that component, we also define our physics. Of course, both are going to be diffusion, but because diffusion implies a little bit of geometric dimension, for example, the out-of-plane symmetry and the thickness, that's why it's kind of unique to here. And then mesh, obviously, because we're going to be meshing our particular spatial dimension. It's going to look very different. Okay. So component 2 is where we define our one-dimensional geometry, right? The mesh for a 1D geometry is going to be pretty trivial. There's only so many ways to cut up a line. And similarly, our physics are going to have different cross-sectional area for here. So it's the same physics, it's the same idea, it's just a little bit of extra parameters that it gives you and kind of tailors to your needs. All right, so the next step is a little bit tricky, so I want to draw some attention to it. Each study, not only do we have two components, we also have two studies. Each study is going to be dedicated to a particular component. So study number 1, when you click into it, it's going to be time dependent, and you only want to select TDS1, which is transport of dilute species 1. Okay, that is defined here. You'll see this says TDS. That is the name that's referred to for this particular physics mode, which belongs to component number 1. Similarly, for study number 2, if you look under the time dependent, you've only selected TDS2, which is, you guessed it, right? Transport of dilute species 2, which belongs under here. Now, you might be scratching your head a little bit about why you want to do that. This is for generality. There are going to be cases later where you're going to want to solve for individual physics modes, even within the same component. So if we're doing something like coupled heat and mass transport, maybe we want to solve for mass transport first, use that in initial condition, and then put in our heat transport afterwards. COMSOL gives us the capability and the flexibility to do that at the expense of a little bit of confusion about what these properties mean to relate to. Okay. The other pitfall is to do with how you're looking at the results. Now, typically when you have the study, by default, the box is checked that you generate the default plot, right? By default, you get the defaults, right? What that means is when you run the study, it's automatically going to populate stuff like, well, what that means is when you run the study, it's automatically going to populate, making a liar out of me, the two-dimensional plots, i.e. it's going to show you the solutions, right? That has that has wired everything correctly for you. Similarly, when you go to compute for study number 2, it's going to generate the default plots, which correspond to the one-dimensional simulation. Now, that has wired together the viewing of the solution with the correct result because we've got these two studies. What that means is it comes up to here and it comes up to the data set, and the defaults have taken care of all this for you. If you're just relying on the default plots, you don't really need to worry about this. But if, for example, you go up here and you start to create your own plots and all of a sudden something isn't looking right and you're kind of confused, it's probably this. That's why I wanted to delve into this a little bit. Yes, I want to delete that. Okay, so the data set is the output from your study, right? Remember, we chose in the previous lecture which study solutions we want to output. That becomes your data set, which you can then access. For this one, right, you're looking at the data set that corresponds to study number 1, solution number 1, and you plot it, and lo and behold, you get your result. For this one, you want study number 2. It's a little bit tricky because you actually have two solutions here. What's happened is that it's taken the solution from study number 1 and just kind of copied it over. So it's not really a useful thing. It's just kind of hanging out there. But what you want is solution 2 bracket 3, which is your one-dimensional solution, and now you can see this. So again, with the default plots, as long as you keep to those, or if you just go here, right-click and go to duplicate, then it'll keep everything and you can kind of tweak things but keep the original wiring. But if you do run into a problem, it's probably that.